The yield point phenomena which is observed in the low carbon steels, it is mainly due to the presence of solute elements, interstitial solute elements like the carbon and nitrogen. Then we have also discussed about the strain aging. The strain aging which strengthens the material and a slight decrease in ductility occurs due to this strain aging. So in strain aging we have two types. One is static strain aging and second is dynamic strain aging. Dynamic strain aging occurs at slightly higher temperatures but below 400 degrees. This dynamic strain aging occurs during plastic deformation. The strain aging that occurs during plastic deformation is dynamic strain aging. Because of this dynamic strain aging, in the stress strain curve, there is continuously fine serrations are seen in the stress strain curve. This is due to the solute atoms which rapidly diffuse to the dislocation core and try to lock them, and the dislocations, they get locked and unlocked, locked and unlocked. So this process repeats, thereby fine serrations are seen in the stress strain curve. This is for the case of dynamic strain aging. And this strain aging can be eliminated by a small amount of cold reduction, less than of about 2% reduction by cold rolling. So this is known as skin pass rolling or temper rolling. This is mainly given for the low carbon steel sheet materials because of the presence of this strain aging during deep drawing or during sheet forming processes or sheet forming operations. An objectional surface is seen, an irregular surface is seen due to the structure strains or the Luder bands. So this causes an objectional surface finish for the formed parts. Thereby, this strain aging is to be eliminated, and this can be done by temper rolling or skin pass rolling just before the sheet forming processes. If the material is delayed even after temper rolling or skin pass rolling for several days at room temperature, then again the carbon and nitrogen interstitial elements, they diffuse and again leads to strain aging. That is, the yield point phenomena again reappears. So in order to form low carbon steel sheet materials, this temper rolling or skin pass rolling has to be given before sheet forming, or as soon as the sheet temper rolling or skin pass rolling is given, the sheet forming process is to be carried out without any delay, or else again there will be a reappearance of this yield point phenomena and leads to the surface defect that is known as structure strains or Luder bands. And the dynamic strain aging behavior, which is seen at slightly higher temperatures but below 400 degrees centigrade. So the main reason for this is these solute atoms, they rapidly diffuse to the dislocation core and try to lock them. And again the dislocations try to overcome these obstacles, and again these solute atoms, they diffuse rapidly to pin down the dislocations. This continuous pinning and unpinning of the dislocations by the solute atoms gives rise to a continuous fine serrations in the stress strain curve. This dynamic strain aging behavior is also known as, it is also related to an effect that is known as Poitevin-Le Chatelier effect. Poitevin-Le Chatelier effect. So this is about the yield point phenomena that occurs in the low carbon steels strain aging. two types, dynamic strain aging and static strain aging, and how to eliminate this strain aging and why is it required to eliminate this strain aging. All this has been discussed. And some portion of the plastic deformation in single crystals, small portion is left over, that is about the kink bands and deformation bands. The next will be the strengthening mechanisms. The main important part is the strengthening mechanisms. So initially I cover briefly about the deformation bands and kink bands. Now what are these kink bands? We have already discussed about twinning, which is another mechanism of plastic deformation, and some of the differences of twinning with respect to slip has also been discussed. One more type which is mainly seen in HCP metals during compression loading is kink band. So what is this kink band? So that will be discussed now. Kink bands usually occurs in HCP metals during compression loading. So during this compression loading, this kink band appears. What is this kink band? When the applied stress is nearly perpendicular to the principal atomic plane, when the applied stress it is perpendicular to the principal atomic plane, the principal slip plane in the case of HCP metal is the basal plane. So when the applied stress is nearly perpendicular to the basal plane of the HCP metal, this type of kink bands are seen during compression loading. The metal shears by the formation of dislocation arrays that produce buckling along the slip plane direction that shears the metal several degrees away from its previous position. So the slip planes, there is slight buckling of the slip planes in the slip direction. So these are known as the kink bands. So the metal shears by the formation of dislocation arrays that produce buckling along the slip plane direction that shears the metal several degrees away from its previous position. The atomic positions, they do not form a mirror image after shear displacement, unlike in twinning, where a mirror image forms in the case of twinning. But the atomic positions, they do not form a mirror image after shear displacement. So this is about the kink bands mainly seen in the case of HCP metals when they are loaded in compression, and that too the applied stress, if it is perpendicular to the main principal slip plane, that is the basal plane, commonly the basal plane of the HCP metals. So this type of kink band is seen. That means the metal, it slightly shears by the formation of dislocation arrays that produce buckling, slight bending along the slip plane direction that shears the metal several degrees away from its previous position. And moreover, the atom positions, they do not form a mirror image, unlike in twinning. So this is about the kink bands. The next is the deformation bands. The deformation bands, it is seen mainly in FCC and BCC metals, but generally not found in HCP metals. So this deformation band, it is mainly due to the inhomogeneous deformation of a crystal results in regions of different orientation. It is called deformation bands. Because of the inhomogeneous deformation of a crystal results in regions of different orientations, that is called deformation band. Deformation bands, it is mainly observed in, generally it is observed in FCC and BCC, but not in HCP metals. So even after repeated polishing and repeated etching, these deformation bands are seen because they represent regions of different orientations. And for the case of a polycrystalline material, microscopic observation is required to observe these deformation bands. And in the case of a polycrystalline material, these deformation bands can be easily formed, or the tendency to form the deformation band is very easy in the case of polycrystalline materials. The reason is because in the case of polycrystalline metals, there are number of grains and grain boundaries which separate the grains. So because of this, there is more number of restrictions imposed by the grain boundaries, or more the restraints imposed by the grain boundaries. Thereby, it is easier for the orientation changes to arise in a grain during deformation. Because of the presence of the grain boundaries, the orientation differences arise very easily within the grains during deformation. So this is about deformation bands. The next topic, the very important topic in the mechanical metallurgy, is the strengthening mechanisms. We have already discussed a few strengthening mechanisms in the previous lectures. Some of the strengthening mechanisms, if you recollect, that were discussed. What is actually a strengthening mechanism? Strengthening mechanism in for a material. A material is said to be stronger if it requires more stress to deform that material. You call a material a hard material or a strong material when it requires more stress to cause plastic deformation. What is the main reason for plastic deformation? Moment of dislocations. Moment of dislocations is the main mechanism for the slip to take place. That is a mechanism of plastic deformation. So any hindrance or any obstacle to the dislocation motion gives rise to strengthening. So for an alloy designer or for a material designer, an alloy can be made stronger if there are some hindrance or some obstacles to the dislocation motion. By creating some obstacles, by creating some hindrance to the dislocation motion, a material can be made stronger. Now, what are the obstacles to the dislocation motion? Some of the strengthening mechanisms which were discussed previously, where the obstacles to the dislocation motion are other dislocations. The dislocations themselves, they act obstacles to their motion. That is one of the obstacles which was covered earlier. So the strengthening mechanism, the name of that strengthening mechanism where dislocations themselves are the obstacles to their motion is strain hardening. So that is covered previously. So strain hardening is one of the strengthening mechanism where the obstacle to the dislocation motion is the dislocation themselves. So other dislocations which obstruct the movement of the dislocations is the obstacle in the case of strain hardening. And second type of strengthening mechanism is the boundaries. The boundaries also acts as an obstacle to the passage or to the movement of dislocation. A grain boundary is not penetrable by a moving dislocation. That means a moving dislocation cannot pass across the grain boundary. It cannot move into the adjacent grain by crossing the grain boundary. So other boundaries, they can be a high angle grain boundaries, low angle grain boundaries, sub boundaries. So all these comes under boundaries which acts as an obstacles to their motion. But among these boundaries, grain boundaries are not penetrable by the moving dislocations. They offer more resistant or restraints for the dislocations, for the moving dislocations. So grain boundaries. Grain boundaries which obstruct the dislocation motion. So larger the grain boundary area, that is finer the grain size, stronger is the material. So grain boundaries was also discussed in the previous lecture. What are high angle grain boundaries? What are low angle grain boundaries? And what happens along the grain boundaries? Why grain boundaries are of higher energy? Why the segregation, impurities, all these impurities, they segregate along the grain boundaries? And equicohesive temperature, where strength of the grain and grain boundary are same at that temperature, beyond which grains are more stronger and grain boundaries are weaker. And below equicohesive temperature, grain boundaries are stronger and grain interior is weaker. And smaller the grain or larger the grain boundary area, higher is the density of geometric dislocations. So all these were discussed in grain boundaries. And moreover, one of the important relation which gives a relation between yield stress and grain diameter was also discussed. That relation is known as Hall-Pitch relation. That is, yield stress is equal to the friction stress plus a constant Hall coefficient, that is also known as a locking parameter for the dislocations, into d to the power of minus 1 by 2. So yield stress is inversely proportional to square root of grain diameter. Finer the grain size, greater is the yield strength. So all this were discussed in the previous lecture, covered under the subheading of grain boundaries. So boundaries are also obstacles to the dislocation motion, because for the dislocation to move into the adjacent grain, it cannot move into the grain boundary, because the slip, it has to change its direction. Next, the third is solid solution strengthening. Solid solution strengthening. Solute atoms, both interstitial and substitutional solute atoms, they also contribute to strengthening. So this also was discussed in yield point phenomena. So how the substitutional solute atoms, they move near to the edge dislocation to reduce the strain energy, and interstitial solute atoms, which are much smaller in size, they form quadral atmospheres. They occupy the positions below the edge dislocation. So how they contribute to strengthening was also discussed. A still more explanation about the solid solution strengthening will be given. And the fourth type of strain hardening is the second phase particles. A second phase particles contribute to strengthening of a material. The second phase particles can be precipitates or dispersites. So these are of two types, second phase particles. They are precipitates and they are dispersites. Precipitates in the case of precipitation strengthening mechanism or precipitation hardenable alloys, which is seen, and dispersites in dispersion strengthening. Dispersites. And the last is about the fiber strengthening, which is mainly seen in composite materials. Fiber strengthening. Strengthening due to the incorporation of fine fibers. So these are the strengthening mechanisms which strengthen a material or which strengthen an alloy. That is, alloy can be hardened or it can be strengthened simply by obstructing the dislocation motion or by creating some obstacles to the dislocation motion, an alloy can be strengthened. So the various mechanisms or the various obstacles for the dislocation motion are the dislocations themselves. So the mechanism is the strain hardening occurs during plastic deformation, where the number of dislocations increase during plastic deformation. So as the density of dislocation increases, they themselves act as obstacles to their motion. So that is the reason for strain hardening which takes place. The second type is the grain boundary. Hall pitch relation was already discussed. Next is the solid solution strengthening. Solid solutions are of two types, substitutional and interstitial. So these substitutional or interstitial solid solutions, they create lattice strains because the solute, it is slightly larger than the solvent atom or it is slightly smaller than the solvent atom in the case of substitutional, and in the case of interstitial it is much smaller than the solvent atom and it occupies the interstitial sites. So because of which lattice expansion or contraction takes place and lattice strains are induced. These lattice strains are interacted by the dislocations moving. Because of this interaction between the lattice strains and the dislocations, the strength of the material is increased. So now what are the different ways by which solid solution contributes to strengthening? There are different methods that contributes strength by solid solution. The first type is elastic interaction. In solid solution, we have different types of interaction that takes place between the solute and the dislocation. The first is the elastic interaction. Elastic interaction. The second one is the modulus interaction. The third is stacking fault interaction. Stacking fault energy. Stacking fault energy interaction. Fourth type is electric interaction. Fifth type is short range order, and sixth type is long range order. So these are the various mechanisms of solid solution strengthening. Among the two types of solute elements, the interstitial and substitutional, interstitial solute elements contribute to more strengthening than substitutional, because interstitial solute elements, they cause more distortion than the substitutional solute elements. The distortion that is created by the interstitial solute elements are of non-spherical type, whereas the case of substitutional, the distortions that are created by the solute elements are of spherical. So these distortions, they cause hindrance to the motion of both edge and screw dislocations in the case of interstitial solute elements, whereas substitutional solute elements, which cause only spherical distortion, they cause hindrance only to the edge dislocations. More distortion is caused by the interstitial solute elements, thereby greater hardening when compared to substitutional solute elements, which causes less distortion, thereby less contribution to hardening when compared to interstitial. Now coming to the various type of solid solution strengthening, the first one is the elastic interaction. Elastic interaction, the strength mainly from this mechanism is due to the elastic stress fields that surrounds the solute atoms. So these stress fields, they interact with the dislocations and cause hindrance to their motion. So this elastic stress fields depends upon the misfit of the solute. Larger the misfit of the solute, larger is the hindrance to the dislocation motion. That is elastic interaction. That is mainly because of the misfit of the solute. The stress fields which surrounds the solute elements, they cause hindrance to the dislocation motion. The second one is modulus interaction. Because of the presence of solute elements, if they cause any modulus change locally, that alters or that changes the modulus of the crystal. So that also creates strengthening because of the modulus difference between the solute and the solvent. The third type of strengthening in solid solution strengthening is stacking fault energy. Solute atoms, they segregate into the faulted region of the extended dislocation. An extended dislocation, it looks like this. Two partial dislocations, in between there is the faulted region. So this is an extended dislocation which has dissociated into two partial dislocations. These two are known as partial dislocations. The partial dislocations between there is a faulted region. Faulted region surrounded by the two partial dislocation. So this stacking fault is associated with some energy that is known as stacking fault energy. Higher is the stacking fault energy, lesser is the separation. Higher is the stacking fault energy, lesser is the separation between the partials. So lesser is the faulted region. And these two partial dislocations, they try to come closer together. Lower is the stacking fault energy, greater is the faulted region. And these two partial dislocations move away from each other if lesser is the stacking fault energy. For a dislocation, for this partial or extended dislocation to move as an unit, it is very, very difficult. If it has to move as an unit, the stacking fault energy should be very, very high, because if the stacking fault energy is very high, these two partial dislocations come closer and the width of the faulted region will be less. If the stacking fault energy is low, larger is the separation between the partials. So it is very difficult for this extended dislocation to move as an unit, because there are many constrictions for this extended dislocation to move as an unit. So the solute atoms, they segregate into the faulted region of the stacking fault. The solute atoms, they segregate into the faulted region and lower the energy. So if the energy is lower, wider is the fault, wider is the faulted region, and more separation between the partial dislocations. So as the concentration of the solute atoms in the faulted region increases, lower will be the energy. Lower the energy, more is the separation between the partial dislocations, more is the faulted region. So there will be more constrictions for this extended dislocation to move, whereby this also contributes to strengthening. So this is about stacking fault energy. Lower the stacking fault energy, wider is this faulted region, more separation between the partials, and it is very difficult for this stacking fault to move, whereby the strength of the material increases. If the stacking fault energy is very high, closer will be this two partials and the dislocation can move easily. It can cross slip easily. Next is the electric interaction. The electric interaction, it mainly occurs or mainly comes into picture only when there is a large valence difference between the solute and the solvent. if there is a very valence difference between the solute and the solvent. So because of this large valence difference, the solute atoms, that electric charge is concentrated on the solute atoms, it is localized, and these solute atoms, they act as charge centers, and these solute atoms are interacted by the dislocations which has dipoles. So greater energy is required. So this is about the electric interaction. So this comes into picture only when there is a relative large valence difference between the solute and the solvent. Short range order. The short range order is when the solute atoms, they arrange themselves in such a way that there are more number of dissimilar neighbors. The solute atoms, they occupy the positions, or they arrange themselves in such a way that there are more number of dissimilar neighbors. This is opposite to that of clustering. Short range order is opposite to that of clustering, where clustering means the solute atoms tend to come closer together or group together over small areas. It is similar neighbors. Solute atoms tend to concentrate over small regions. Because of this short range order or clustering, for the dislocation to move, it requires more energy. Why? Because it disturbs the local ordering. Thereby, the strength of the material will increase. In the case of short range order, the solute atoms, they group together in such a way that they have more number of dissimilar neighbors. And clustering is also grouping of the solute atoms over small areas. So for a dislocation to move, it disturbs or it alters the local ordering. Thereby it requires more energy to bypass it. And short range order, it is mainly seen in some type of alloys. Example, super alloys, nickel based alloys, where the formation of ordered regions creates anti-phase boundaries. APB stands for anti-phase boundaries. They are also associated with some energy. So for a dislocation to pass through this requires more energy, and moreover ordering increases with increase in temperature. Thereby the dislocations to bypass these obstacles or to move through this is very, very difficult. So this long range order, this will be discussed under the subheading of superlattices. So only briefly I have touched about this long range order, but this in detail will be discussed under the subheading of superlattices. Whereas all these elastic interaction, modulus interaction, stacking fault energy, electric interaction, short range order, all these were discussed, and all these are the mechanisms of solid solution strengthening. Either one of these contributes to solid solution strengthening. Among this, elastic interaction, modulus interaction, and long range order, these three, elastic interaction, modulus interaction, and long range order, they are temperature insensitive. That means they occur for long ranges. They are insensitive to temperature. Whereas the stacking fault energy, electric interaction, and short range order, they are of short range. That means they are temperature sensitive, these three. So this is about the solid solution strengthening, the various mechanisms in solid solution strengthening. So for a material, the strengthening, it may be any one among the strengthening mechanisms that were discussed. Either it may be from strain hardening, or it may be from the grain boundaries, or it may be from solid solution strengthening, or any of this. So the total strengthening constitutes the sum of individual strengthening mechanisms for that alloy. So now coming to the important strengthening mechanism, that is the second phase particle. So the second phase particles are obstacles to the dislocation motion. They hinder the dislocation motion. These second phase particles are two types. One is the precipitates and second is dispersoids. So the two strengthening mechanisms are the precipitation hardening mechanism or precipitation strengthening mechanism and dispersion hardening. Now we'll see what is the difference between precipitation strengthening and dispersion strengthening. So briefly about the precipitation strengthening mechanism, or what alloys undergo this precipitation hardening, whether all alloys are subjected to this precipitation strengthening or there are any restrictions for the precipitation strengthening. I hope some of the topics might be covered in the last semester, precipitation strengthening during the physical metallurgy. But still, once again, I would like to briefly explain about the precipitation strengthening mechanism. So precipitation hardening, so the main requirement for an alloy to be precipitation hardenable is it requires sloping solvers. Sloping solvers means solubility should increase with increase in temperature and solubility should decrease with decrease in temperature. So this is the main requirement for an alloy to be precipitation hardenable. And moreover, the precipitates that are formed in the precipitation hardening, they must be coherent with the matrix. Then only the strength comes from, or it creates more strains, thereby more hindrance to the dislocation motion, thereby more stronger the alloy. So sloping solvers is the main requirement. I consider example of aluminum copper alloy. Aluminum copper alloy which undergoes precipitation hardening. So sloping solvers means a material or an alloy should undergo a decrease in solubility with decrease in temperature, increase in solubility with increase in temperature. So this is a small part of aluminum copper alloy. Temperature and composition. So this is the sloping solvers. The solubility increases with increase in temperature. As temperature increases, more the amount of solute goes into the solution, and with decrease in temperature, the solute is rejected. That is, the solubility decreases with decrease in temperature. So this is known as the sloping solvers. The solvers line which should have a slope. So initially the first part of this precipitation hardening is the alloy. It is to be solutionized. It should be given a treatment known as solutionizing. This solutionizing treatment is mainly given so that all the solute goes into the solution. So homogenization takes place. The solute goes into the solid solution and it is in single phase. Then after solutionizing, the alloy is quenched. Quenching is mainly to retain the supersaturated solid solution, and then upon aging, the excess solute comes out in the form of precipitates, fine precipitates. The size of the precipitate, it increases with time. So this is about precipitation hardening. So not all alloys undergo precipitation hardening because of the requirement of sloping solvers. The solubility should decrease with decrease in temperature, and moreover the precipitate, it should be coherent with that of the matrix. Whereas in the case of dispersion hardening, it is also known as mechanical alloying, because metal matrix powders and inert oxide particles like yttria, Y2O3, thoria, alumina. So these are the inert oxide particles. The volume is about 2%. 2% of volume of this inert oxide particles, they are mixed with metal matrix powders. Inert oxide particles, which constitutes of about 2% volume, they are mixed with metal matrix powders, and they are consolidated by powder, compacted and consolidated by powder metallurgy techniques or powder metallurgical routes. So the size of this yttria, it is less than 25 micrometers. So they are mixed in a high energy ball mill, and they are consolidated and compacted by powder metallurgical techniques. So since this oxide is inert with respect to the metal matrix, even at higher temperatures, the dispersites, they do not undergo coarsening. The coarsening is very less or very small. They undergo only very small, lesser extent of coarsening even at very high temperatures. Whereas in the case of precipitation hardenable alloys, the precipitates, they coarsen at higher temperatures. By means of solid state diffusion, the precipitates, they coarsen. Coarsen means they increase in size, and the number comes down, number of precipitates comes down, the size increases. Thereby they provide less restrictions to the dislocation motion, because the coherency of these precipitate particles is lost as they coarsen. So this is the main difference between the precipitation hardenable alloys and dispersion strengthening mechanisms. In the case of precipitation hardenable alloys, the alloys which have a sloping solvus and the precipitate need to be coherent with that of matrix is required. Whereas in the case of dispersion strengthening mechanism, one can produce infinite number of dispersion strengthening alloys theoretically. Why? Because it is only mechanical alloying, mixing of metal matrix powders with the inert oxide particles, and then by ball milling and then consolidation by powder metallurgical techniques and forming the product. There is no coherency between the dispersites and the matrix in the case of dispersion strengthening alloys, but there is a coherency between coherency or lattice matching. It is also known as lattice matching between the precipitate particles and that of the matrix. And moreover, when compared to strengths, precipitation strengthening alloys or the precipitation hardening mechanism contributes to a greater strength when compared to dispersion hardening mechanism. Precipitation hardening mechanism, they contribute to a greater strength when compared to dispersion strengthening mechanism. But the one advantage of dispersion strengthening mechanism is, even at higher temperatures, the dispersites, they do not coarsen, they do not react with the matrix, they are not soluble in the matrix even at higher temperatures, and they go very less amount of coarsening. Whereas the precipitates, they undergo coarsening at very high temperatures, thereby the strength drops down. So this is the main difference between dispersion strengthening mechanism and precipitation strengthening mechanism. So now I just draw a figure which shows the strengthening mechanism of from solid solution strengthening, precipitation strengthening and dispersion strengthening with respect to temperature. Temperature and the strength of all these three mechanisms. So this is the strength and the homologous temperature. Homologous temperature, it is given in Kelvin. It is a ratio of the operating temperature to that of melting point. So this is homologous temperature. This is for a pure metal which has less strength when compared to that of solid solution. Solid solution strengthening. Pure metal, where the strength comes down with increase in temperature and it is having less strength compared to solid solution strengthening. For an alloy which has only solid solution strengthening. Next is we have the precipitation strengthening. This is about the precipitation strengthening or the precipitation hardening, which is having higher strength, but the strength drops down at about greater than 0.6 of the homologous temperature because of the coarsening of the precipitate. As the precipitate coarsen at higher temperatures, it loses its coherency, thereby the strength comes down. Whereas dispersion strengthening, it is comparatively relatively low strength when compared to that of precipitation strengthening, but even at higher temperatures at about 0.8, it can withstand its strength, it can retain its strength because the dispersites, they do not coarsen or they coarsen very lesser extent at higher temperatures. So this is about the three types of strengthening mechanism with respect to temperatures and their strengths. Dispersion hardening. So among all the strengthening mechanism, precipitation strengthening has the highest, it contributes to a greater strength when compared to other strengthening mechanism. Next is dispersion strengthening. It is lower than precipitation strengthening, but when compared to precipitation strengthening at higher temperatures, it retains its strength. The main reason is the dispersites, they coarsen to a lesser extent when compared to the precipitates, which coarsen very rapidly at higher temperatures. The least is the solid solution strengthening. Strain hardening and grain boundary strengthening at higher temperatures, the strengthening mechanisms are of no use. As at higher temperatures, strain hardening is relieved because of other processes which come into picture like recovery, recrystallization. And at higher temperatures, grain boundaries are weaker. Thereby, among the other strengthening mechanisms with respect to temperature, precipitation hardening has the highest strength, but its strength drops down with increase in temperature, and dispersion strengthening, it can still retain its strength even at higher temperatures. Okay.